Hey Spencer, you can always ask me a programmer question.
How do you deal with burnout?
I go into academia.
Yeah.
That's how I deal with burnout. I haven't hit it yet.
Oh, I have.
It happens. You just become administration if you're burned out, right? How do you deal with burnout? I guess you got to do something other than work, and I think that in actuality, going to work is easier than going to class because at 5 o'clock you're done, right? And I have all these expectations of that I need to be doing other stuff outside, you know. So, going to real work is a joy, right? If you don't have to actually do stuff. When I was in grad school, I always had the sense of, hey, you should be working on your thesis instead of enjoying the day off or stuff like that. So, but yeah, just get out and do some other stuff.
Okay.
Go throw a ball with your
Yeah.
friends.
Spencer, I'll teach you.
Okay.
Got my glove in my pocket.
John can catch. He was a catcher.
I was actually.
He was a catcher, so he could do it.
I played everything. Whoa. Once in a while. I was a pitcher when I was really little. Did really bad.
Played everything.
So they moved me to catcher. Put me in the infield.
Did you pitch in softball too?
Well,
Fast pitch?
I have 3 sisters. I have both in softball. So
You pitched?
yeah.
Fast? Ooh.
Okay, did
I've also
you get
got
the
to be
paycheck
by softball.
for the undergrad?
We can talk to Carol about that.
Okay.
I don't know.
Because,
I don't deal with money and stuff.
yeah, no, you get one too.
I know.
Yeah.
It goes into my fund.
Oh, okay.
I heard that was coming. All right. Yes, Jonah.
So you said that if we took your file and put it in our directory, then we shouldn't get any end of file linked list or printing or whatever. Mine still prints a question mark and 1, but it's not weirdly formatted. It's actually question mark 1. Would it be
Question mark 1?
you want to look? It's simple.
I don't want to. So I think one of the things that you guys will probably have to deal with is the fact that if you put it inside of a loop that says while not end of file, that really the way you should do that is you should read the character first before your while loop one time, and then at the end of your loop you need to read the next character because that's when you will want to check for end of file. Because otherwise, you check for end of file, you read a character, it's actually the end of file character, it's going to add it to your list of characters, and it'll go, before, right? So you need to do that. You need to read the character as the last thing that you do inside the loop. So you do it before you enter the loop, assuming that there's at least one, which it'll still get end of file when it does the check, so you'll at least skip it. But, I'm always going to give you a file that has some data in it, right? Okay, other questions on the homework? Do I need to survey you? How many of you have got part 1 done? Okay, so that's 2, 4, 5. So then the question of how many have part 2 done is 1, and then part 3. Come on, Spencer, why aren't you done? Okay, so your goal should be that you should have part 1 done very much soon, right? When is this due? The 9th, right? You might say, hey, I got 3 weeks. Well, not quite, right? Or I guess you could count it as 4. Right? Today's what, the 14th? 1, 2, 3. 3 more weeks, but we're going to be gone during Thanksgiving, and who wants to program during Thanksgiving when you could be eating turkey and stuffing or ham or whatever it is you eat? I eat carrots, celery. Okay, so, right, this is going to be the most difficult assignment you've done in this class, so you should start on it early. Right, Josh? Yeah? Yeah. What? The shell taught you that. If you're not in operating systems, you will learn that the shell will get you. Start day one. Start day one. Day one. What is a shell? What do I need to do? How do I do C? All right. No questions? Comments? Good. Do we have any dad jokes? Because I'm always up for those. Jonah, you're an epic fail. No dad jokes. Why did the frog cross the road? Because he was riding a chicken. Chicken crossed the road. Dad joke, 100%. That's what I do. All right. All right. So I got a couple warnings. We're not going to worry about those right now. I'll try and fix them later. And I was editing this while I was before class. So a couple things that I wanted to talk about. Bryce, do you want to hit the lights since you're closest? That's great. Right there. All right. So thus far, when we've been talking in class, we have been sort of malloching all the memories, right? So we always ask for memory, but we haven't talked about sort of giving it back up, or how do you resize the amount of memory that you ask for, right? So currently we always ask for memory, right? We allocate it for new objects. We do stuff with our objects, and then our program exits, right? And we just don't worry about it. So this example has a couple of different functions that we're going to talk about. So let's just go through the flow of the program, and it might be toy in its complexity and why it's doing certain things, but it's not necessarily toy 100% all the way. So there are some interesting things that we're going to do. So if we look here, we allocate a pointer, right? malloc1 allocates us exactly 1 byte, and then we set that 1 byte to 0, right? So we have a null terminated string that has no characters in it, right? Not very exciting. Okay? Then we allocate some memory. We allocate 100 bytes, right, for memory. We declare a variable called done. We set it equal to 0. Our while loop says while it's 0. And if we look down here, eventually we set done equal to 1. If they enter the text done, right, so they type done, and like it's going to quit. Not too bad. All right, so we do a scanf looking for a string for memory, and we figure out how long it is, and then we declare an array of integers that, so Sterling of memory is the text that they typed in, right? So we allocate an array of integers that has the same number of indexes as memory. So, right? So if I typed in hi, hit enter, right, it's going to allocate 2 bytes because the length of hi is 2. Right, so I have an array of 2 integers, right? Integers are all 4 bytes. And there's a typo. It should be the length size of an int, right? So we'd actually get errors on that. Okay, So then it loops through every single element of the character array, right? I equal to 0, I is less than certain length of memory, I plus plus, right? And assigns the integer at index I equal to the int value of the memory at I. So what is that giving us? What is the int value of a character? It's the ASCII value, right? If we write it in hex, it would be, I think, what, 61 hexes an A or something like that? It's pretty close. Right, so we're getting the ASCII values of the array, right? Assigning, or of the characters, storing them in the array that happens to be called ints, right? And then we initialize some sum equal to 0. Again, we loop through however many elements are in our array, and we calculate a sum, and the sum is based on the previous sum plus the int value at a particular index, and then it's modding it by 255. Okay? So one notion that we could call this, we're computing a hash of the string, right? Because we're just modding it. Typical, an actual hash, you would probably do something like, you might shift sum over by like 7 bits or 5 bits or something like that, and then do the mod. Either way, right, we're computing some sort of hash based on the sum of all of these characters that we're entering in. Okay? All right. So at this point, we've allocated our array of integers. And if we look at this, we're not actually using that anymore after this point, correct? If we've allocated it, we haven't really given it back. So at this point, we should actually call a function called free. So what free does is it says that I'm no longer using this memory inside of my program. You're giving it back to the what we call allocator so that it can use it to allocate for either a different process or for your own process when you need it. Right, so as one of the jobs that your operating system does is that what we call manages memory, right? And we can actually run programs where we are using more memory than we actually have. So let's say we have 8 gigs, we might say that we're using 1 terabyte of memory. Well, we can't actually like pretend like there's no physics involved, right? So if you're pretending like you're using 1 terabyte of memory, what we end up doing is you take the memory that you wrote, and the stuff you're actively using you have actually in RAM, so maybe you're 4 gigs or 8 gigs, and then the rest of it is going to get written to disk, whether that's an SSD or just a regular hard drive. Right, so we end up pretending like a program might have as much memory as it thinks it has, but in reality, the OS handles the what we call swapping out of memory to disk and vice versa, right? Swapping it back in when it needs to. So if we don't do this free, right, as our program runs, it's going to keep allocating block, and then allocating another block, and allocating another block, right? Until it's allocated so many blocks that we are out of memory, right? And we can actually allocate so many blocks that the operating system just fails. So I don't know how many of you who are not in operating systems noticed, but apparently one of my operating system students wrote a program that had an infinite loop, and it kept allocating memory and running processes until we ran out of memory, and it caused the server to crash. And then Kyle said, you guys are going to get banished from here, so we're making a new server, so that way when you guys blow it up, it doesn't blow up like all of your home pages and PHP and MySQL and things like that. All right, so the good thing to do in here is to actually say, I'm going to give back the memory, so that way the program can keep running without what we call having a memory leak, where it just keeps adding memory.
So,
Now,
is
yes.
that what happened to Spotify? Did you read that? That they, like, over the 8 days, there's a terabyte of just garbage data.
That could be, or Spotify could just be terribly programmed. I mean, so I didn't actually look into Spotify's because I don't use Spotify and I really don't care about Spotify. So, I mean, it wasn't something I particularly looked into. But it could be something where they are caching. So there's sort of like cache at the internet sort of level where, let's say I want to grab the Google logo, for example, right? So I might go grab the Google logo and just store it locally. So that way I don't have to go out to the internet, which is relatively really slow compared to what my hard disk is. Now, what I would imagine Spotify is doing is they're saying, hey, you listen to these 20 streams, or whatever you call them in Spotify link. I don't know what they're called. Are they called streams? What? Channels? I don't know. What are they? Like, can't you listen to multiple things on Spotify? Playlists.
Songs.
Well, group of songs. So playlists, right? So it might be you have 10 playlists, and what they're saying is, oh, while we're just sitting here doing nothing, let's go grab, you have 10 playlists, let's just go grab them, cache them locally, right? And just keep doing that, so when you want to listen, we can instantly give you the, next 20 minutes of music without any delay, and then maybe we'll keep streaming that one in also. So, again, I didn't actually look at it, but I'm imagining. I'm using my brain and thinking, right? Could be. I don't know. I'd have to look at it. All right? So as we can see in this one, right, it's really simple because all we need to do is free the memory that we've allocated for this one pointer. Now where it gets to be more complex and where you have to start thinking about things is, let's suppose we have a structure that has a bunch of different elements that exist within it. And maybe each one of those elements points to, another block of memory. So we can't actually free the main one and then go and free each one of the ones from it. We have to go in reverse order, right? So if I had a structure, they'll look like this, right? And let's suppose that I'm done looking at the encodings or the characters or the left or the right? Let's say I removed a node from my tree. Well, then I would have to go through each one of those and free the memory for those before I could come and free the memory for the huff object, right? Or the huff structure. Right? Because I need to go through that. Well, how do I know if I'm done with the next or with the left or with the right? I don't, right? So that's the issue where you have to deal with is I need to manually keep track of where are all these pointers and when are they done. And you can hate on Java or love Java, but the one benefit of Java is that it automatically does this. It automatically keeps track of how many things are pointing to this, and then there's an additional sort of weirdness where you can have an object that points to another object, that points to another object, that points back to the first object. All of them are referenced, but it may be that we have no external pointers that come into that group of objects. Right? And so if we don't have any, then we'd say, oh, each one of them has a pointer to one thing, let's keep all of them in memory, when in fact it's not what we call reachable from any of the pointers that we have in our main program. And Java takes care of this by a method called mark and sweep. So basically it starts at all the things it knows about. It keeps going, marking things that it finds on the way. And all the things that it finds, it copies to a new location. And then it just sweep, right, gets rid of all the ones that are left over. So anything that's not referenced, right, we get rid of. And you can actually call the system dot, I think it's GC for garbage collection, to automatically go through and collect garbage. Now, that's a time-consuming process, but sometimes you want to do that so that you don't have it, because randomly the garbage collector will just get called, right? Oh, I'm going to call garbage collection right now. And maybe that's at a point in your app where you really don't want it to be called, whereas you're doing something not important, right? User's not interacting with it, you might call garbage collection periodically just so that you've got it out of the way and you don't do it dynamically on the fly. Whew. There we go.
So if you don't dereference any memory and you exit the program, that just dereferences it right there.
Yeah, so the benefit that we've got so far is that every program that you guys have been running has not been something that needs to be running for 24 hours a day, 7 days a week, 365 days a year. Right? So we don't have the issue of dealing with running out of memory or having memory leaks. Now, the problem that you typically get in, like if you're running a web server, right, you want that to be running all the time, or you have you know, some page that you want to be running that's running PHP, right? So you don't want those type of processes to run out of memory. Yeah, so the benefit is you exit, right? All the memory gets given back at that point. Okay, so any questions on what we should do, what we haven't been doing? Right? Okay. You guys always feign like you know what you're talking about, and then I ask you a real question. That's what happens. Okay, so does anybody know what the index function does? Anybody? Anybody? Let's look. When in doubt, if you don't know what a function does, you can look it up. So the index, or our index, right? We'll take a. So the first argument is a char pointer. The second argument, they call it an int, right? It's the representation of a character, right? So you need to automatically take a character and cast it into an int, or it'll automatically cast it, which I believe is why I got one of the reasons why I got a warning. All right, and then it returns a char pointer, right? And I believe, okay, it returns a pointer to the matched character or null if the character is not found, right? So it returns null if we can't find the character inside of the string that we're looking at. Otherwise, it returns a pointer to that. So if it's at index 27, right, it's going to point to the original base plus 27 characters to get to the 27th index. Ah, shouldn't have been editing it. Holy cow. Come on. Okay. So we check to see, like the internet is speaking right now. All right, so we're checking to see if there is a bar inside of the string, right? So if it's not null, that means there is a bar in there. And then let's look what we're doing right here. So line 28. So the length that we're looking at is equal to 1 plus the length of result plus the length of memory. A string length, right? So what's the, initially, what is the length of result? What did I set it equal to at the top? 0, right? It has a length of 0 because the very first character is the null character. So it's 1 plus 0 plus the length of memory, right? So if I type I, memory has 2 characters in it, right? So we've got 1 plus 0 plus 2 would give us 3. And then we have this function called realloc. So what realloc does is it will take the current array that you have and it'll allocate it to a new size, but all of the data that was already in there is going to stay the same. Right? There's also another function called calloc or clear alloc. So it'll set all of the indexes in your array to a particular value. So if you want them all to be null, right, you can say calloc, and you can say 0, or if you want them to all contain A's or whatever it is you want them to contain, it'll initialize them to a particular type of value. So realloc is going to say take result, which is my current pointer, and extend it to a new length. And so was it initially 0, so now it's going to allocate at least 3 bytes for it, right? And then we're going to use the stircat function. You guys should be familiar with stircat because you're going to need to use it if you're in your program, right? We talked about on Friday how, right, you can use the pointer inside of the, right, you can use the char pointer encoding in order to store what is the encoding as we trace down our tree. In each recursive call, depending on if you went left or right, you would append a 1 or a 0. If you want to do it backwards, a 0 and a 1, right, however you wanted to do that. Right, but you need to use stircat to concatenate the old string with the new digit that we're going to add to it, right? So that we can do our recursive call. Correct? Does anybody have issues with that? Questions? All right, so strcat will concatenate one string onto the other, add a null terminator at the end. All right, they have to be null terminated strings. So I know these are null terminated because when you do the scanf, it automatically terminates with a null. And at the top, I set result equal to 0, right? Result bracket 0 equals 0. So I had that one was null terminated also. Right, if I didn't null terminate it, right, it could have random garbage in it, and I could just read it and use it however I please, but right, that's how it typically allocates it, is just random stuff. So you need to make sure you initialize things equal to 0 if you want them null terminated. Unless you use calc, which will initialize them for you.
So this is a really stupid question. In fact, this might be the stupidest one I asked. But is that how like they managed memory back in the 60s? Like when they didn't have a lot of it?
Is what how you allocated memory?
Just like how they managed it. They would have to basically delete everything and start over.
Well, okay, so it's not a stupid question. It's just I don't quite know. What do you mean how they had to delete everything and start over?
Well, they had to remove all the bits, like using a free or whatever, and then just having to rewrite over it.
Yeah, I mean, your memory is being used like that all the time anyway.
Okay.
Right, so your program is always, right, so if you were to take operating systems, right, you would learn about how you have a certain amount of memory, and they used to have what we call different segments, and you would take a segment and you would swap it out to disk and not. So all of the modern operating systems use what we call pages, and so a page might be a 512 kilobyte block, and so when you start running one program, it will load some of those blocks into memory, and then when you try and access one that isn't loaded, it generates what we call a page fault. So the page fault will tell the OS that I need a page in memory, and so the OS will allocate a virtual page in memory, and if there was something already in that, it'll swap it out to disk for you. If you have free memory, it just allocates a new page and loads the data from disk, and then resumes the program as if it had never done anything. But if you look back in history, right, there were a lot of different ways that they managed it. One of them was using the segments. So you'd have one that's called the code segment. We had a data segment and a stack segment. So these are all different pages and indexes in memory. And they would basically take the segment and they would add an offset, and they did a little bit of shifting so they could get a 20-bit address when we only had 16-bit pointers, right? So on the 16-bit machines. So back then, I mean, yeah, memory was a lot different in the way that it was managed. But as the systems have evolved, we've added this ability to use paging so that processes transparently don't actually see paging when it actually happens. But if you were running bare metal, right, you'd have to manage this yourself, right? So you can just run a program bare metal and not use any of the operating system libraries. That's what an operating system is, right? It's just a program that's running.
So it was pretty much a miracle that we got to the moon using less than a meg.
Well, but those computers weren't doing a lot.
Okay.
I mean, if you think about what is a computer that is running for the Mars Apollo mission, right? What is it actually doing? It's not very much.
Oh, okay.
And even if you look at, so at some point when you're developing hardware for a system like that, you need to say, okay, here's the hardware we're going to use. We don't care if there's newer stuff. We're going to use this, and we're going to test it, and we're going to test it, and we're going to test it. Because you can't just say, oh yeah, that broke. Let's go put another one in space.
Yeah.
Right? I mean, they do, right? If you look at what happened with Hubble, right? Everybody seen like what happened with Hubble, right? So there's like a measurement error, and so they had to build in correction because it cost how many billions of dollars to build Hubble, and it was cheaper to launch up into space and put a correction part in rather than rebuild the entire satellite. So it's kind of amazing what they ended up doing after they figured out that, yeah, everything's blurry. That kind of sucked. So does that answer your question?
Yeah.
Brandon?
Yeah.
I mean, it is amazing, right, that any of this works, but it does, and we just incrementally got up to this point. Okay, other questions? Right, so here we're talking about what we have inside of C. Now, when we add on C++, which is like C with some other stuff, and we'll talk about that a little bit in class for the rest of the semester. So some of the add-ons that were added in C++. Then we'll get to see that there's a different function for C++, which is called delete, which will automatically sort of call, we have in C++, like in Java, we have what are called constructors. So they allow us to do what we want to do when we create an object. But Java automatically manages the deallocation or deleting of data. Now C++ does not, so we have this anti-constructor, which would be a, anybody want to guess? What? Destructor, right? Deconstructor. Yeah, destructor. Right? So they allow you to, when a object is being freed or deleted, right, they allow you to say, okay, what objects do I need to delete within this one when my current object is getting destroyed, right? It's like I'm blowing up, you push the red button so that all the stuff happens that is supposed to happen. Right? So we have destructors that we'll define inside of C++ that allow us to free up the memory that we need to free up, because that's an issue. That's something that you guys completely miss when you are programming in Java, which is good, right? Less mistakes. But it's bad in the sense that you need to understand, like, how does this actually working on the back end. So, this is showing an example of stir cat. And then it does a stir n compare, right? So, a couple of the functions that you should be using, I'm not going to take off if you're not using them, but you should use the stir copy and stir compare, but you should be using the stir n versions, right? So if you look at anybody who talks about security, they say, why are we still using stir copy and stir compare? There's very bad reasons for using these, right? I'm teaching you them here, and we'll talk about some of those reasons, but you should be using the ones that are limited to a specific size. And does anybody know why we're supposed to use a specific size? Buffer overflows. All right, and actually Windows 10 has some mitigations in it, several different mitigations. So mitigation is a way to solve the problem without actually solving the problem. It's like, how do we stop rivers from overflowing? We build little dams all along the edges of them, right? And it doesn't actually stop the problem, but, you know, sort of fixes it. So we'll talk about those, probably not today. But the last thing I wanted to do today, we'll talk about what a buffer overflow is probably next time, is, so a particular iteration of this loop, what are the factors that are going to determine the runtime of this particular loop?
Memory that you allocate.
Okay, and how is that memory, how's the memory that I allocate based? The length of the string, right? So I'm basing how much memory I'm allocating based on the length of the string. So we've got one dimension of, if I have a string that is of length n, I'm allocating n times 4, right? Size of an int is 4 bytes of memory. So that's one dimension of analyzing this algorithm. Okay? What is another dimension that we need to analyze?
Whether that string has like a lot of those bars or not.
Well, whether it has a lot of the bars or not, maybe like how far in the bar is, right? So when we use the index, right, and we'll get to that one, right? That is having to scan every single character, right, until it finds a bar character. right? What else?
String compare.
We got string compare, but that's fixed at of length 4, right? So we look at our string compare, it's string and compare. So this is always going to take at most 4 operations. It's going to stop at 4 characters and say, yes, they're equal or not, right? So it'll never go past that. So that's constant time, right? O of 1, which is 4. What else?
I feel like since we created a variable named size, but we never used it.
We shouldn't have it?
Yeah.
Okay. So, we've got the let's delete size camp. What else have we talked about in class?
I feel like we should use size.
Oh, we've got somebody else in a different camp saying, let's not delete it, let's actually use it.
Well, yeah, I agree with that.
Oh, so you're like both sides of the fence now? Let's not delete it, but delete it. Okay, so we're not going to delete it.
And instead of checking for stir length, each time with size.
Okay, so what is the problem with the for loop on line 15? What is the runtime of that loop? We've discussed this before. It's n squared. Does everybody know why it's n squared? So what is the runtime of stir lang? N. And how many times are we calling it? N, right? So if you were to look at the stir lang function, right, it's going to check the character, is it null? Check the next character, is it null, right? Or 0, not null, right? It's going to keep doing that for n characters. So the runtime of this loop is, right now, O of n squared. And this loop is the same, right? It's also O of n squared. So maybe we could combine the thought of, let's use size. How could we rewrite this? We could use size in here, right?
Yes.
And now it's not O of n squared, it's what? O of n. Right?
Same thing in your malloc. I'd give size.
Yep, because that malloc now is going to take, well, if we think of how it's going to take n time to compute how long it is. And then when you actually allocate the memory, well, that could take n, or it could be a constant amount of time. The actual way it does is it actually does a subtract on how much memory you have for some of them. Otherwise, because there's a function called break that'll just subtract some space away from your memory limits. So it sets limits, and then you say break, and it'll just increase those memory limits. But yeah, it'll take some time. So we can use, again, size here to reduce that n that we have in our time. Okay. Anywhere else where we can be more efficient? Yeah, so on 29 we're using, well, for this one, okay, results, we don't know what that is right now, but here we can use size. But do we know how long Result is? How long is it to start? 0, right? At the very top, it's 0. So let's suppose we save that information. And then down here, instead of declaring a new variable, says how long it is, maybe we could just calculate it, right? Because Sterling is just like terrible as far as runtime. So result size is going to be, we're going to basically add to it size. And then the actual amount of memory that we allocate needs to be 1 bigger than the old size, right? So we need to allocate, so we add on the new size that we're going to add to it, and then we allocate 1 more. We do it because we need to allocate for the null, which doesn't count as far as our original size, right? And then we can call reallocate on that new length, and then every time, right, we're updating how big that size is. Yes?
Why does the reallocate take 2 arguments?
So the first argument is the original pointer, and then the second argument is what size should it be? So that's the second argument. And then it returns a pointer, and I think that's because in case it has to allocate a new memory location and copy all the data, then you can use that new pointer in order to reference the memory from now on. All right?
I've got another stupid one.
You got another question.
I do. How does C differentiate between a pointer and multiplication?
How does C differentiate the difference between a pointer and multiplication?
Yeah.
Well, that's part of the language is to figure out when the context of when an asterisk occurs.
Right.
So it knows by the context whether or not to reference the object that you're looking at as a pointer or as multiplication.
Okay.
Because if you look at like how we would use an asterisk, we would have it bound to something, and if we had an arithmetic operation, right, then we'd be missing something if that asterisk binds to the dereference,
Yeah.
right? Because you'd have object, dereference, we need an operator in there, so it's going to complain that, hey, you're trying to multiply a pointer by something, whereas you wanted to dereference it and maybe add it or multiply it. You're going to have to add parentheses to give it that context and add another operator. So there's never a case where we are using the asterisk and we can't tell if it's a pointer or if it's an integer. And they've written the language such that that is the case.
Okay.
Yeah. If you were an automata, we could talk about the grammar used to create it. And it's a BNF grammar. They don't want to talk about that because I didn't make them. I have a book that's like the Pascal, and it shows the Bachnis-Nauer normal form version of the grammar, and it's not exciting. Something you'd do in a compiler class. Okay, so we're almost done, right? So if we look at the running time of the program before, right, we had lots of operations that were n, right? We had some of these loops that were n squared, right? And if we look at how much memory it took up, we saw that the array called ints was however many characters were entered, right? So one iteration of that loop, based on the number of characters entered, is going to be, what is the runtime for that case? Before we had the optimizations, how much runtime did it take? Based on n is the length of memory. What was it before? It was
N squared.
n squared, right? So we had an n squared, we had an n, right? This is not based on that. This is 4. And so our runtime for one loop was n squared for that. Plus, we have this other function, right? We had stir cat. So what is the amount of time for stir cat? That's based on two things, right? We'll call them M. Let's call it P and N, right? So the stir cat function is based on P, which is the length of result, and N, right? So because that's not the same variable, right? It's not O of N, it's O of N plus P, right? We'd have to write that in our runtime analysis. So we'd have, the original one would be O of N squared plus O of N plus P, right? Because they're different variables. And we can't just lump them together because one could be way bigger than the other, right? N could be 5, right? We could have or 2, right, when I said high. But the size of result could be 1 billion. Well, which one's going to be bigger? Which one is going to take longer? 4 squared or a billion? That's clear, right? A billion. Right, so we have talked about, everything we've talked about before was, we always had one variable that was the determining variable. But we can also have more than one, right? So we could have 2 variables, 3 variables. So it might be O of n squared plus O of p cubed, right? And then it just depends on which one of those is bigger, will determine the runtime of that function. All right, so that's it for today. Next time we will talk about buffer overflows, why you should use stir n copy, stir n compare, stir n cat. Why should we use those? Why do buffer overflows exist? Maybe a preview into 301, which you might find exciting, maybe. So, all right.